hope to make some sense for you out of that little montage you just saw there as we move into graphs of reciprocal functions, secant and cosecant. First, we want to review what the cosine function looks like. As I produce a graph on the cosine from 0 to 2 pi, there's one period of cosine. And now its reciprocal function, secant x, we're going to graph that right in the same window. And notice what happens as I produce the graphs of secants. The reciprocal values, as the cosines get smaller, the reciprocals get bigger. And that makes sense if you think about, for example, what happens when you flip or take the reciprocal of 1/2. Well, you get 2. And if you take the reciprocal of 1/10, you get 10. If you take the reciprocal of 1 over 100, you get 100. That makes sense. And so as cosines are going to approach pi over 2, where we have a 0 value, the secants won't have a 0 value. So even though you're not going to see it on the graph, you're going to visualize a vertical asymptote occurring right there. There's going to be a vertical asymptote right there. And now the reciprocal values are negative, and they're going to be very big numbers, but they're going to get smaller and smaller. And these two graphs are going to meet, you can see where, right there. Because right there, they'll both have a value of -1. And then the symmetry of the cosine function dictates that the symmetry of the secant function will follow suit and will produce the other half of what I like to call these things, little things, horseshoes that you get when you graph secants and cosecants. There's another vertical asymptote appearing, and we're going to get another half of a horseshoe coming to meet us up here. Now we're going to repeat this process for sine and cosecant. And as I graph sine for you, I ask you to try to visualize what cosecant is going to look like. Where are the vertical asymptotes going to be? And where are the maximums and minimums of sine and cosecant going to coincide? Where are the horseshoes going to be? So here we go. There it comes. There's the first asymptote was the y-axis, and there's the first, it's a minimum for cosecant at the maximum for sine. And we go off to complete the horseshoe as sine hits pi. There's our first vertical asymptote. I hope you can visualize it. And now where's the graph of the cosecant function going to come from? Well, that's right, those negative signs. The reciprocals are going to be very, 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 very negative because the sine values are very, very small negative. And here it comes. And there's the other half of the horseshoe. So the period of sine and the period of cosecant are going to be exactly the same, 2 pi. And that's also true of the period of secant and the period of cosine. Now we'll take a quick look at this on a larger scale. Here's our old friend, the sine function. We're looking at several periods. And here's the cosecant overlaid on top of it. And you can visualize where the vertical asymptotes would be, where the sine is 0. And you can see where the shared maxes and mins. A max of a sine is going to be a min of a cosecant. And you can see why the shapes are horseshoe shapes, because they follow the reciprocals of sines. And similarly, here's cosine and here's secant. And it looks exactly the same. In fact, it is. It's just everything is shifted pi over 2 to the right because of the relationship between sine and cosine. Those exact same relationships will hold between secant and cosecant.